Okay, scroll a little bit more. So here's 3. Again, you should be checking the assignment from last night. My work against yours. If there's problems, we can ask some questions after we finish scrolling through all the answers, but this should have been fairly straightforward, right? You're just using the little formula charts that we made in class. So here's 4 and 5. So we're on to the back page. Notice the graphs for 4, 5, and 6 are really different looking than the graphs for 1, 2, and 3. Cube root graphs look different than square root graphs. So when you're drawing your picture, you got to make sure that you're aware of what type of function you're graphing so you draw the right kind of picture. Yeah, Olivia? That's a -1 and +1. So this was just the number that I wrote and I screwed it up, so I scribbled it out. Okay. Hopefully it looks more like a scribble than anything else. But I can see the 0 that you're thinking there. This is a very circular scribble. Okay, I'm going to scroll down a little bit more. Madison, have you figured out what the domain and range is then for all these? Yeah, right. So they're all cube root functions have the same domain and ranges. Doesn't matter what else is going on in the cube root function. If it's a cube root, the domain and range should be easy. It's always the same. You don't have to think about it any more than identifying that it's a cube root function. And I'm going to scroll down just a little bit more so you can see the last picture. Any questions from this assignment? Things you'd like to talk about or go through again, or going once? Harley? Do 5? Sure. So 5 is y equals 2 times the cube root of x minus 2 plus 3. So we'll start by identifying our values for a, for h, and for k. You good there? So I'll make my xy table, and because this is a cube root graph, the way I'll pick my x coordinates is like so. Good there? And the way we'll find our y coordinates is like so. So this is just using from our notes. So I have -6 for the first point. 1 for the second point, 2, 1 plus 2 or 3, and then 10. And then here we have -2 times 2 plus 3, so that's -1. -2 plus 3, so that's +1. 3, oops, 2 plus 3, which is 5. And then 2 times 2 plus 3, which is 7. So if I go and plot this, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, and then 1, 2, 3, 4, 5, 6, 7. So -6, -1, 1, 1, 2, 3, 3, 5, and then 10, 7. And because this is a cube root function, I know I'm going to connect both ends, and both ends are going to get an arrow. Okay with that? And then obviously the domain and range for all cube root functions is -infinity to +infinity. So I'll just say that aloud. We mentioned it earlier when we were kind of going through things, but does that feel okay? Okay. So again, these two tables of kind of formulas, very important to kind of make sure that you're using when you're doing these graphs. That's our tool for doing this. The two tables are different for cube roots and square roots, so you have to make sure you're using the right table of formulas for each one, but these were in the notes. They're very important. When you're graphing, you're definitely going to want to use those. Yeah. We want to look at the answers for 6. Okay. Did anybody else have any questions from this assignment? Okay, good. Overall, this should have been not too bad, right? Maybe we made some mistakes or whatever, but when you see, hopefully you see what you did, and hopefully it was just like, oh, I used the wrong table, or oh, I found the wrong value of A or something. You know what I mean? Should have been relatively straightforward. Today, what I want to talk about is simplifying radical expressions. So, for example, we want to deal with like how to do something like this and get an exact answer. So that's what we're going to be worried about trying to do today, is figure out ways to simplify expressions that have radicals in them. So this is going to be a kind of, might be something like we'd want to be able to do come the end of the day. Before we get there, though, we're going to have to introduce a couple of rules that we're going to use, and then talk through a little bit of an analogy of a way to think about some of these kinds of problems. So the first thing I want to do is define the product property for radicals. So what this says is the nth root of A times the nth root of B is equal to the nth root of A times B. So for example, if I'm taking the cube root of 5 and multiplying it by the cube root of 7, I can think about that as the cube root of 5 times 7, or just the cube root of 35. Everybody okay with kind of what that rule is saying? Just describing to us how we can multiply two radicals together. What's the very important part about this rule, though? Is that you have to have the same kind of radical. If I'm multiplying a square root and I'm multiplying a cube root together, this rule does not describe to you how to do that. That's something we'll have to deal with a little bit later on in this chapter. So the big takeaway here when using this rule is that you have to have the same kind of radical. So I can multiply two cube roots together, No big deal. I can multiply two square roots together. No big deal. I can't multiply a square root and a cube root together using this rule. We will talk about how to do that, but not today. Everybody okay with that rule? It's a fairly simple one, right? We've used this before when dealing with just square roots. So the next one is the quotient property for radicals. And what this says is the cube root of the fraction a, or the nth root of the fraction a over b, is the same thing as the nth root of the numerator over the nth root of the denominator. So for example, I can take the fifth root of 2/3, and I could rewrite that as the fifth root of 2 over the fifth root of 3. Everybody okay there? We see how this rule is working, that I can just take the radical of a fraction and break it into the quotient of two radicals, right? So an important thing when we're simplifying radical expressions is to know when we're finished. So a final answer for a simplified radical expression should have just one radical in it. All the radicals in there should be reduced, and we should have no radicals in our denominator if there is one. So we know how to combine radicals into one using these two rules, the quotient property or the product property. What I want to talk about right now is how to reduce a radical. So again, we can combine radicals together using a quotient property or product property that we just kind of saw some quick little examples of. I'm more interested in talking about right now, which tends to be the more difficult skill for students, is how to reduce a radical. Okay? And to talk about that, I want to do this by analogy, because eventually I'd like to get to the point where we can reduce these radicals without really having to show much work. And the easiest way to do that is to kind of think about it as this kind of a problem that I'm going to describe to you. Okay? So what I want to talk about is exchanging currency. So let's say that we have 9 quarters. And we go to the bank and we trade those quarters in for larger denominations. What am I going to leave the bank with? So we're going to have 2 $1 bills and then 1 quarter still. Let's draw it this way. Everybody agree with that? Why is that the case? Because 4 quarters make $1, right? We call this an exchange rate. Everybody okay with this idea? This should feel like elementary school math, right? Where we're just talking about exchanging coins for dollar bills and stuff. So let's say then that we have this problem. I have the 4th root of 2 to the 9th. The index for our radical is the exchange rate. So what this is saying is it takes 4 of a number underneath the radical to get 1 of that number outside the radical. So do I have at least 4 2's underneath my radical? Yes. So what I can do is I can exchange 4 of those 2's to make 1 2 outside the radical. Since I exchanged 4 of them, I now have 9 2's have changed to 5 2's. Is everybody okay with that idea? Okay. Can I do an exchange again? Yes, because 5 is still bigger than 4. I could do a second exchange. And how many 2's would be left this time? 1, right? Can I do another exchange? No. So we would be done. So we can just write this as 4 4th roots of 2. Yes, Nia. Of course. Does that feel okay there? Do we see how this was still the exact same problem as the currency exchange problem we just did a moment ago? So the exchange rate, it takes 4 2's under the radical to get 1 2 outside of the radical. So I have to subtract 4 2's from underneath, leave me with 1, and I'll add 1 extra 2 on the outside. Is that okay? The nice part about thinking about the problem in this way is that these are largely problems we can now do in our head, right? We don't have to write a lot down. Let's do another. Sound good? So let's say we have the 3rd root of 5 to the 11th. What's the exchange rate in this problem? 3. So that tells me it takes 3 of these 5's underneath the radical to get 1 5 outside of the radical. How many 5's can we move, or how many 5's can we get outside the radical then? How many times can we do that trade, that exchange? 3 times. Everybody agree with that? So I'm going to have 3 5's outside of the radical. How many 5's are going to be left underneath the radical? Not 8, 2. So the problem that we're doing in our head is I'm taking 11 and I'm dividing it by the exchange rate. Right, exactly. So when I did that, I get a quotient of 3 with a remainder of 2. This 3 tells me the number of 5s I get outside the radical. That's the quotient. And the remainder tells me the number of 2s I have left under the radical. Or the number of 5s, excuse me. So that's the problem that we're kind of doing in our head, right? As we're just doing that little division problem. Let's do it another. Yes? Notice here that I didn't do steps. I just went straight to the final answer, right? If you wanted to, you can multiply these things back out now and write it this way. Okay, let's do another. So this is the square root of 3 to the 9th times 7 to the 8th. So this one I'm going to do a couple more steps on because it's a little bit different than the previous ones. First thing we need to do is identify the exchange rate for the problem. The exchange rate is not 0, it's not 1, it's 2. Nope, because it's a square root, right? Okay. So I'm going to write this. Then using the product property, I can do this. Everybody agree with that? Okay. So let's do the square root of 3 to the 9th. How many exchanges can we do? 4. Why 4? So why 4 is because we're taking the number 9, the exponent, and dividing it by the exchange rate, which is 2. When I do that, I get 4, remainder 1. So I'm going to get 3 to the 4th on the outside, and then 3 to the 1st on the inside. So this 4 is that 4, and this 1 is that 1. So this is the 9, this is the 2. Where is the 3?
Yeah, the second 3.
What do you mean, where's the second 3?
Like, that's in the square root. Like the 3 to 1.
You're talking about this one? Yeah. It's because we have 1 3 left over. We're going to do the 7 separately. Yes, we're doing them as 2 separate pieces. That's exactly right. Now we're going to do the 7s. Okay. How many exchanges can we do with the 7s? 4. So I'm going to have 7 to the 4th. And then how many 7s are left over? 0. What is any number other than 0 to the 0 power equal to? It's equal to 1. So anything to the 0 power other than 0 gives you 1. So this can really become, I'm not going to do that, but 21 to the 4th square root 3. I would need a calculator for the 21 to the 4th part. Harley's going to do it for us. Tell me what it is.
194,400.
There. Thank you. Let's do another. Is this starting to feel... Okay. So before we go and do the next one then, if you said you were okay with the first one, does that number... Hi, Father. Thank you, sir. Appreciate it. Does this number really matter with what we're doing? These numbers I've circled in blue. No, they're just a placeholder. It doesn't matter in terms of the exchanging or how many exchanges I'm doing or any of that stuff. That number doesn't really matter to me. I'm not even really looking at what it is. It's just the object that I'm making my exchanges with. Could be tacos or shrimp cocktails or basketballs or whatever. It doesn't matter, right? So when I look at a problem like this one right here, the only two numbers I care about are these ones. I care about the exponent, and I care about the index. If I take the exponent and divide it by the index, that's going to give me all the information I need to do the reducing. So if I take the index and divide, or the exponent and divide it by the index, I get 3, remainder 2. The 3 tells me the exponent on the number outside the radical. And the remainder, the 2, tells me the exponent inside the radical. That's what we're doing each time. Okay, so let's try another. So we're going to do this all, try to do this all in one step. Okay? So we're going to do 3 little division problems to do this. The first division problem, I'm going to use 5 divided by 10. Okay? What is 5 divided by 10? 2. What's the remainder? Okay. So I'm going to have 2 to the 2nd. And then underneath my radical, I'm going to have a 2 to the 0. What's 10 divided by 2? 2. So that's why it's 2 to the 2nd. No. The first 2 is because it's a 2. Now you're okay? All right. Next up, I'm going to look at the 7 divided by 5. What is 7 divided by 5? 1. So I'm going to have a 3 to the 1st. And what's the remainder? 2. So I'm going to have a 3 to the 2nd underneath the radical. Now I'm going to do 18 divided by 5. What's that? 3. So I have 5 to the 3rd. And what's the remainder? 3. So I'll have 5 to the 3rd underneath. And then we use our calculator to kind of clean this up at the end. I can't do that in my head right now. It's been too many class periods. Does that feel any better? Okay. What if we do this? No, definitely not. What's different about this or this problem than the previous ones? It's not written as the product of powers of primes, right? What? Madison, I missed what you said. You kind of mumbled it. No, it is one of these types of problems. We just need to get it into a form that looks a little bit more familiar. So what I'm going to do is I'm going to start by doing the prime factorization of 24. So what two numbers can multiply to give us 24? Any two numbers other than 1 and 24. 6 and 4. Okay? Are either of those prime numbers? Do we know what I mean by prime? 16? 16 is not. A prime number can only be divided or is only divisible by itself in 1. Is 6 a prime number? No, because it's divisible by 2 or 3, right. So what two numbers can multiply to give us 6? 3 and 2 or 2 and 3, doesn't matter the order you write them. Is 2 or 3 prime? They're both prime. So we're done with that branch. Now let's look at 4. 4 is not prime because it can be 2 and 2. And we're done there because we just said 2 is a prime number. So what I have is that this is 2 to the third times 3. And now it's just like the previous problem, right? We just had that extra step of having to do a prime factorization to get it into the form that we can use our exchange rates. Okay. So, can I do anything here? Yes, right? What can I do? So, 3 divided by 3 is 1 with remainder 0. Can I do, next thing we'll do is we'll look at the 3's. 1 divided by 3, we can't do anything like that, right? We just get 0 remainder 1, basically. So we'll just put the 3 back under there because there's no exchange that we can do. So this just turns into 2 root 3. Is everybody okay there? Kate? Sure. Okay, let's do another. What if we have the 4th root of 12 times the 4th root of 28? Well, let's first write it as 1 radical. Okay with that? Okay. And now let's do the prime factorization of 12. So what two numbers multiply to give us 12? 6 and 2. Okay. Is 2 prime? Okay. Is 6 prime? No. What? Okay. And then we'll do the same thing for 28. Okay, 7 and 4. Is 7 prime? Okay, 4 is 2 and 2. Okay, so we can write this as the 4th root of 2 squared. Well, let's just do this. How many 2's do we have? We have 1, 2, 3, 4 of them, right? So I have 2 to the 4th. And then I have 1, 3, and 1, 7. Everybody okay there? It's probably going to be the why make more work, right? Can I do any exchange here? Yes. What can get exchanged? The 2's. So 4 divided by 4 is 1. And then obviously the 3 and the 7 don't have enough exponent to do any exchanges, so I'll just multiply them together. And we have 2 times the 4th root of 21. Justin. Of course. We good there? Okay. Let's say we have the 3rd root of 96 divided by the 3rd root of 20. What should I do here? So let's do this first and write it as a single radical. That's fine. Notice 96 over 20. Can that be reduced? Certainly can, right? Should be easy to see that it can because both the numerator and denominator are even. So at minimum, what can we take out of each of them? A 2, right? So 96 divided by 2 is 48. And 20 divided by 2 is 10. What about now? Can we do any more reducing? We can take another 2 out. 48 divided by 2 is 24. And 10 divided by 2 is 5. Can we do any more there? Okay. So I'm going to write this as cube root 24 over cube root 5. Let's do the prime factorization of 24. What two numbers multiply? In fact, we did this already, didn't we? So I'm just going to use our result from before. 2 to the 3rd times 3. What's the prime factorization of 5? It's already prime, right? We don't have to do anything with that. Okay. So what exchange can we do here? The 2 to the 3rd, right? So 3 divided by 3 is 1 with remainder 0. So I have this. Everybody happy there? But we're not done because we have a radical in the denominator. And we said we didn't want any of those in a final answer. So who remembers what we can do to get a radical out of our denominator? This would have been something you talked about last year in your geometry class when you talked about sine, cosine, and tangents. Let me help jog your memory. So if we had like a right triangle and say this is our angle theta that we're concerned with, if we did sine of theta, that was opposite over hypotenuse, right? But we didn't like our final answer to be formatted like 1 over the square root of 2. What did you guys do to that to get it in the form that we used? It wasn't the Pythagorean theorem. Multiply that by square root 2 over square root 2. Because when we do that, we get the square root 2 over the square root of 2 squared. And how does the square root of 2 squared exchange out? To just be a 2.
But or is it just coincidental?
Yes. Okay. So we needed to multiply the top and bottom by something so that we could make an exchange in the denominator, right? So let's look at the denominator in this problem. I have the cube root of 5. How many 5s do we have to have in the denominator to do an exchange? 3. Everybody agree with that? How many do I have down there right now? 1. So how many more do I need? 2. So I'm going to multiply the top and bottom of this by the cube root of 5 squared. Everybody okay there? Now if we do the exchange in the denominator, I'm left with just 5, right? Can I do any exchange in the numerator? No, because I have a 3 to the first, only one 3, can't exchange that, and a 5 to the second. 2 5s, I can't exchange that. So I'm left with 2, and then if I just multiply 3 times 5 squared, I get 75. So we can leave that as our final answer. Is that okay, Harley? Sure. Yeah, these are reasonable difficulty test questions. That's why we're going through these slowly. Well, we'll make sure we include the directions, and this is the first time you're trying it, Madison, which is also makes it like hard to remember what you're doing because you haven't had any practice yet either, right? So like that makes a big difference. Everything seems harder until you try it in the homework, right? Because you can't really learn math without doing any. And right now we're just mostly sitting and listening and thinking. We haven't really done anything ourselves yet. So that makes a difference too, okay? But we'll do lots of practice on this because I know that this is a difficult skill, okay? So I know this is one that takes some practice. And again, I'm showing lots of steps for some of these. We'll certainly condense down some of these steps, but the first time you're seeing it, I think it's important you see like how the numbers are changing and why they're changing. And as we understand that better, we can kind of condense some of these things and do them in our head. But the first time seeing it, I'm trying to write down almost everything that we're doing. Okay, so it seems longer than maybe it needs to be. Many of these, once we're good at them, we can do really just straight to the end without having to do much. All right, let's just do that same problem, but we'll do the reciprocal of it. So I'm just going to kind of skip a little bit here because I'm using the same numbers as above. So I know exactly how these things are going to reduce. Is that okay? Because it's the same reducing problem as the previous one. I just used my previous work to skip to the reduced part. And then I'll do my prime factorization. Do we see an exchange to do in the numerator? What two numbers do I need to look at to do the exchange, since nobody's answering? I need to look at the index and the exponent. There's no exponent written on the 5, so what is the exponent there really? 1. Very good. Since 1 is less than 3, can I do an exchange? No. So the numerator is done. There's nothing more to do up there. Now let's look at the denominator. Again, I'm going to compare the exponent to the index. Can I do an exchange with the 2's? Yes. How many 2's are going to come out? 1. Where is it going to go? Into the numerator or the denominator? It's got to go in the denominator because that's where the radical is. How many 2's are left after I take that 1 out? 0. Okay, so now let's look at the 3's. So I compare the exponent to the index. What's the exponent on the 3? 1. Since 1 is less than 3, can I do an exchange? No. So that 3 is just going to stay down there. Is everybody okay here? We still have one more thing to worry about, and it's because we have a radical in the denominator of our fraction. So I'm going to need to multiply the top and bottom of this fraction by something so that there's no radical left in the denominator. I don't want to do 3 cubed because I already have 1 3 underneath my radical. So if I put 3 more in there, I'd have 3 to the 4th. That's too many. How many 3's do I want exactly in my radical? I want 3 3's exactly. I have 1 down there already, so I need 3 squared. Is that okay? We see why, though? Oh, I see. So we want cube root of 3 squared. Because now if I count, I have 1 and then 2, 3. I have 3 3's now under my cube root. Does everybody see that? Okay. Is 3 3's enough to do an exchange? Yes, right? Because what's the exchange rate? 3. Okay. So how many 3's can I take out? 1. And how many are left? 0. Okay. So no more radical. And then my numerator is just going to be that. And if I combine my numbers, I have the cube root of 45 divided by 6. Maddie?
How did you get when you first reduce the fraction?
The 5 over 24?
Like, right, yeah. How did you get it?
So I just stole my work from up here. Because this is the same problem, it just flipped.
Oh, and how did you get that in?
Oh, okay. Well, I looked at 96 and 20 and noticed that they were both even numbers, so they're both divisible by 2. So if I divide 96 by 2, I get 48. If I divide 20 by 2, I get 10. 24 and 10 are also both even. So I could do it again. I have 24 then, and 5. And there's no more things that divide both of them. So I was done. That's kind of just the way I thought about it. Does that feel okay?
Yeah.
That's okay. I'm glad you asked. We're happy to go back and re-explain things, fill in some gaps. Again, the steps are important that you understand what I'm doing to go from one place to another, because there's a lot kind of going on, right? It's all should be easy arithmetic that we're doing, but making sure we're keeping track of like what the numbers are and where they're going and what they mean. That's kind of the hard part. Notice we're not doing anything much worse than like, dividing 2-digit numbers or like adding and subtracting, or, like we're not doing any complicated things here. Arithmetic, we just are doing kind of a lot of it, right? We probably have time for one more. Let's do one more. Actually, let's not do that. Let's do 54. Okay. So first things first, let's see if we can do any reducing. Can we reduce 128 over 54? Yes. How do we know? They're both even, right? For sure we can reduce two even things. So 128 divided by 2 is 64. And 54 divided by 2 is 27. Is there a divisor between 64 and 27? Number that divides both of them? Yeah. I can't think of one. So let's do the prime factorization. If we missed one, we'll see it when we do the prime factorization because they'll have a factor in common. But the smaller these numbers are, the easier the prime factorization is. So I like to try to do at least as much reducing as I see that's obvious first. And if I have to do a little bit more after I've done the prime factorization, that's okay. It's not a big deal. All right, so 64. What two things multiply to give me 64? 8 and 8, okay. And 8 is 8 prime? No. Okay, what are two things that multiply to give me 8? 4 and 2. We said earlier that 2 is prime. Is 4 prime? No, 4 is 2 and 2. So I have 6 2's there. We good there? Now let's do the 27. Two things that multiply to give me 27. 3 and 9. Okay. We said 3 was prime easy earlier. Is 9 prime? No. What is 9? 3 and 3. Everybody okay there? Okay. Now let's look for some exchanges. Is there any exchange we can do in the numerator? Okay. What can we do? Okay. If I look at the exponent and the index, since the exponent is at least as big as the index, I know I can take something out, right? How many 2's can come out? 1. How many 2's will be left over? 2. Everybody happy there? Now let's look at the denominator. Can I do an exchange there? Again, I'm going to compare the exponent to the index. Since the exponent is less than the index, there's nothing I can do there. So I'm just going to recopy it over to the other side. Everybody good there? The last thing now I need to worry about is if I have a radical in the denominator, which I do. So I need to take care of that. How many? I have a fourth root of 3 to the third, right? How many more 3's do I need to add to that so that I can exchange? I need one more 3. Everybody agree with that? Because I have a 3 to the third, and I can exchange when I get to 4. Everybody okay? So I'm going to need one more 3. So I'm going to multiply the top and bottom by the fourth root of 3. So I have 3 3's here and one more there. That gives me 4 total 3's. So I can do an exchange, right? That'll give me 1 3 on the outside and no 3's left underneath the radical. So I just have a 3 now. In the numerator, I'm going to have 2 times the fourth root of 2 squared times 3, or 2 fourth root 12 over 3. Is that okay? Right. We're going to stop here. I think we're out of time here in just a minute. I'm not going to give you guys an assignment here this weekend. Catch up on your other things. I'm sure that you have a lot of stuff going on. We'll get an assignment and some time in class to work